Good afternoon, dear students. Can you hear me?
Yes, I hear.
Okay, then let's start. Today, we are going to discuss the position and displacement within theory of machines. Okay, here we are. So in our last lessons, we complete the vector calculation. We finished that. So today's topic will be position and displacement analysis, which is an important part of the theory of machines. Because what we learned until now, you can imagine we are dealing with a mechanism, and the mechanism means certain components in certain connections and in certain motion. So that means we have components and we have motions. Motion means, first of all, position and displacement, then velocity and acceleration, and later on, of course, the forces. So therefore, now, before we start, okay, I have to share the screen with you. I shouldn't forget it. So I will make some, okay. Is also. So then I hope you see the PowerPoint, huh? Can you see that?
Yes.
Okay, thank you then. Okay, everything's okay, so we can start. So the position and displacement analysis. This is the topic we are going to talk about. So you may remember we talked about 4-bar mechanism, 4-bar linkage mechanism. So you see here the 4-bar. This is the in blue color. This is the initial position of the 4-bar, and we set here the initial position, the red one. Okay, because the motion is in that direction. So let's use the okay, pencil. So motion is, you see, in that direction. So in that direction, therefore, so the initial position is here A, B, C, D. So, and after a certain motion, the angular motion, let's say the phi here, so it arrive B prime, C prime, because the points B and C are changing its position. So A and B is already grounded. That means fixed to the ground. So therefore, there is no motion regarding A and D, but B and C are moving. So we assume that B moves in the position B prime, and C moves in the position C prime, like you see here. So, and here also. So motion, of course, we use the mechanism on one side for the motion to transfer the motion, on the other side to transfer the power. But first we are going to deal with the motion. So the motion means, first of all, the position. So position, that means initial position, and then, of course, if the initial position is changed, that means there is a motion. So the B and C, that means the A, B, C, D, initial position. That means, let's say, the initial position. And if there's a motion, which we are observing here, angular motion regarding the AB, which is crank, you know, this is, we call crank here, crank. So crank, so moves from the position AB into the position AB prime. And since there is a coupler between B and C, this motion transferred to the point C. The motion motion starts with AB, and A is fixed, so B is turning around the point A. That means this is a circular motion, as you see here, circular motion. So with radius AB, and since B is connected to the point C, C is also moving from the position C to the position C prime, and CD as a member, as a link, is connected, is grounded at the point D, these members. So therefore, C is also, DC is also making a angular or circular motion like this. Huh? But we don't know the angle here. Huh? This is psi, let's say. We applied the angle. This is the angle we applied. We defined, let's say, 60 degrees or 40 degrees or 30 degrees, whatever. We gave this angle, and then, but we don't know what's happened here. Of course, we have an angle also here, but so our interest is to know that. I mean, to be able to calculate it. So in such a mechanism, let's say, let's use the color black. Let's say this crank is it here? Okay. So the length of crank is, let's say, A, and the length of coupler is B, and length of follower is, let's say, C, and this distance here between A and D we defined as D. So that means if you have a mechanism, because we are talking about the analysis. So analysis means we analyze. So known, what are the known? Known is A, B, C, and D. So, and let's say also known is the phi, because if we apply a certain, if we apply the motion with certain angle, so it must be also known. And find what we are going to find. B prime, C prime, and C, and also the angle here between are also interesting, but I will talk later about it. So that means we know the initial position. This is A, B is C, D, and we are looking for the new position for a given phi angle. New position, this is A, B prime, C prime, D. So, we are looking for that. So, the initial position, we call this is the position, and the final position is also position, but in between, there is a displacement. So, determine the position of all points and links, and the driver links is positioned. This is the driver link here. We will call it driver link. So, driver link. Determine the displacement of all links as the driver links are moved. So this is what you are seeing here. It starts very simple, but later on it will get complicated. So why we are learning that? Because if we apply such a mechanism in a machine, so the mechanism will apply certain motion and transfer certain motion and the power. So we have to know about the any point on the mechanism, about any point we have to know the velocity, position, velocity, acceleration, and we are also interested the forces acting on the points A and B, because we have to check whether it will work or break or any misfunction, and also all those things. But first of all, we start with the displacement, position and displacement. So let's come here and say position of a point. So first of all, position of a point. So vector form an origin to the point. So let's say any point here, we have here the X and Y coordinate system. Position of a point means the magnitude of the vector and the angle. Let's say if we talk about this vector here, and we need the magnitude, which is here, let's say 34 millimeter position vector, therefore millimeter or meter, and this is the angle here. So, and the angle is, let's say 45 degrees. So then we know the position of this vector. Actually, we consider also all these links as a vector. This is a vector here, and this is a vector here, and this is a vector here, and so on. And this is also a vector. Let's use another color here, or let's say let's take the blue one. So this is also a vector here, connected. So if it is like this, then we can say total of these vectors must be equal 0 for the time being. For a certain time, that means for instantaneously, the total of this vector must be 0. That means here if we say A, and this is B, and this is C, and this is D, that means A as a vector plus B counterclockwise plus C as a vector plus D as a vector is equal to 0 because it's closed. So it's a closed chain. That means there is no disconnection between them. Okay, so in form of vector we have considered. Then let's continue. So angular position of a link. So this is the angular position here. That means here we set the position of a point. So let's say there's a point B. In order to define the position of a point B, so we need the magnitude as well as the angle. So then we call angular vector between 2 points on a link to a reference axis. So this is the reference axis here. Let's indicate that the reference axis, our reference axis in horizontal direction, vertical direction, we have the reference line Y. Okay, so then linear displacement. So displacement from a point to the others, like so a point moves from I lose the cursor. So linear displacement vector between initial positions and final positions. So this is the initial position and the final position, and the vector in between. So let's say this is this one, or this vector here. Linear displacement vector vector between initial positions and final positions. And we can say delta R, for example, here. We can show in that way. Let's say our A, the point A, and this is the position here, B, and it moves from B to B prime over a circle, because a circular motion come to this point, B prime, B prime. There is a new position here. So from the position to this position, a new position, and this is delta, let's say, here's C is displaced. Let's say this delta R B is equal, delta R B is equal delta R vector R B prime minus vector B. So, and delta RB can be given as a magnitude, and the angle also, I mean the position, can be given in that way. So this is linear displacement from one to the others, like this. So rotational displacement. Rotational displacement, then we have a rotation, rotary motion. So like we consider the angle, like delta theta, here delta theta, here in between. So let's say this is the delta theta, delta theta. So is equal delta 4 minus delta 4 prime. And delta theta is, let's say, clockwise. 17.3 degree. We are saying clockwise because it is the motion is clockwise here. You see, this is the motion here. B is moving from the point B to the B prime, and then C is moving from the point C into the position C prime. So therefore, in the direction of clockwise, we have difference, I mean the as angle delta theta. So angular vector between initial and final position. This is the initial position here and the final position. So let's have an example. Determine the displacement of points A, B. So let's have another color here. The red one is better. So determine the displacement of points A, this one here, A, and B is here. So as the link shown is displaced here, as the link shown displaced 30 degrees counterclockwise. Counterclockwise, that means in that direction. So this is, counterclockwise. Okay. And for that, delta theta must be 30 degrees. Delta theta 2. And this 30 degrees means in counterclockwise. That means in that direction here. So, and we have to find the position, new position, A and B, regarding A and B. So in that position, 30 degrees means this is a circular motion, around this point. Here the point, let's say the O, let's say the point O, around the point O. This member is a rigid body. This yellow one is a rigid body. Number 2, and moves from this position, from the position OAB to the position A prime, B prime, O, for example. And then let's have another color, blue one. So then the new position of A must be a circle around O regarding the A. So must be a circle. So then 30 degrees, let's assume that this 30 degrees is somewhere here. But I think it seems not correct. So I have to change it, correct it a little bit. But you can use the your equipment to draw it. I mean the ruler and the other devices you need. So here Let's take it. Where is it? Here. Okay. So this is the point, our point here, A prime. A prime. Okay. So, and of course, if we know the A prime, we can easily find the point B, because B is also B has to also move on a circle with the center of O, like this. And if you know, the point A prime, we already define it, and we can easily find the position of the B. This is using a protractor here from the center to from the center A prime to this curve, and here A must be somewhere here. Pardon, B prime must be somewhere here. B prime. Okay, then the new position is like this, here. So, more or less, this is the new position of the member 2. And this is, of course, not so good. This one here, I will take it out and I will must be like this here. And so here somewhere. So I also have to take out this one and this also. So this is the new position of the member 2. So you see, I said at the beginning of our lesson, we will deal with geometry, many geometry, analytical geometry, and trigonometry, and so on. So in this example, we have exercised that the position of the member 2 consists of 3 points O, A, B. If we turn it in the counterclockwise 30 degrees, this member will have a new position, and the new position, to derive the new position, it is very easy for us. Okay, so for that I said, you may remember now, so in the fundamentals we already mentioned it, that we will deal with geometry and we will derive we have a protractor and we have a compass and ruler, and we will use that. And I mean, you have to do that. What we are doing now, you should also do that. Compass and protractor, ruler, you have to use. Okay, so let's then come the next picture. So we have here the graphical position analysis. So this was more or less, we said we can calculate it. I mean, we have here the 180, and we have here this is the 80, and if we know that here, this is say the analytic calculations. So therefore, we can easily say here, if we know the here this is the 60 degrees, and this is the 80, and this is 180, and how can we calculate this distance here? So can you do that? So how can we calculate this distance here? AB. A, B is AB is equal question mark. How can you calculate the AB?
Hocam, we can use sine if we have the angle and the hypotenuse.
Right. We can use actually very easily the cosine theorem, isn't it? Let's say this is, let's assume that this is x. So x. So then we can write this equation. We learned that already. X squared is equal 80 square plus 180 square minus 2 times 80 times 180. Okay, 180 times cosine 60. So can somebody calculate it? I need the result.
Professor, may I ask a question,
Yes.
please?
Did you calculate it?
No, I didn't. I just want to ask about the angle. Is it supposed to be 15 plus the 45, the 60 to have the angle? Or am I
Yeah,
wrong?
this is the 60 degrees, yes.
Okay. And another question, may you tell me how did we multiply it by 2? From where did the 2 come from?
This is simple equations. I mean here 80 square plus 180 square minus 2 times 80 times 180 cosine 60.
Yeah, but I didn't figure from where did the 2 come from. Is it from the rigid body or how exactly?
You mean this? Oh, no. You mean these two here?
Yes, exactly.
It comes from the cosine theorem. So you remember the cosine theorem?
Yes, of
So the
course.
cosine theorem is if you have such an angle like so, such a triangle like this, and let's say this is the 60 degrees. So and this is 180 millimeter, and this is the 80 millimeter. 80 millimeter. We don't know this length here, so we can calculate it. And in order to calculate it, if we say, let's say this is A, B, C, and then we can write this equation. Cosine theorem is like this: A square is equal B square plus C square minus 2 times B C times cosine 60 here, since it is 60. Okay? You should know that from the high school, I mean, but we repeated already in our last lessons.
Yeah, I thought because it is a b square plus c square minus cosine 60. I forgot. I'm very sorry.
Minus 2 times b times c times cosine 60. Since this is 60, the angle is 60. So,
Okay, thank you.
you are welcome. We had actually we had it. So here belongs it. Where is it? Here the vector calculations, and here we said here. So in our last lesson we discussed it. The analytical method. Use the triangle. So this is a triangle. Those are the angle here. Like here this C, and this is the A, and this is angle B. And then we write C squared. If you write the C squared is equal, and the other parameter of the angle A squared plus B squared minus 2 times AB times cosinus C. And if we want to write the B, for example, want to calculate the B, then we can write B squared is equal A squared plus C squared minus 2 times A times C times cosine. What is the angle related to the B? This is the B. We have to write here B. So in the same way, we can calculate the B square, we can calculate the C square, we can calculate the A square. It's it is always the same. And we have here, if we know the two angle and two, let's say the length of the triangle. So we can using these equations, or using these equations, or using this and this one. Also we are able to calculate the rest unknowns of the angles. Okay, let's come to our calculation. So we had here I can use the calculator here, and I can show you. But I expect you do it. This is not so complicated.
Hojam,
So
we did it already. The answer would come as 156.2.
Okay, 100.
56.2.
56.2 millimeters. Okay, so I trust it. This is a simple calculation. So then, okay, then we can write here 156 here. Let's write it. Okay, here 100. So 156.2. So then we can draw the angle here, 30 degrees, isn't it? 30 degrees and 30 degrees, and we know the length. I mean we know all the length, OA, OB, and AB. So then using our compass we can easily draw. So this was the analytical way of calculation the new positions, and here the graphical position, the graphical way of to find the position using the graphical way. And here, if we are, let's say, if our driver here or crank move from this position into the position here, let's say the angle here phi. So graphically we are going to draw the position of C, new position of C. So then the position of B is now in the new situation, position B prime. So what is the position C? So how can we find the position C? So we know already that the point C is moving on a circle. On a circle with the center of D, like. And so on, huh? We can. So on. And if you take our compass and where is it? If you take our compass and draw a circle with the length BC, maybe in taking a center of B prime. So then like this, so without calculation, then this point is the new point of C prime. And this is the C prime here. So then this position here will be the initial position of DC prime. So we can also draw this line here to connect the B prime and C prime. So then we have this new position. Okay. So that means the position at the end of a certain motion, the new position we can find in two ways. One of them is the analytical way. We can calculate, we make the calculations, and the other one is we need only to draw. And the same we can do also here. We don't need, if we want to say, draw the new position, the final position, we don't need to calculate the distance here in between A and B. So we can, using the protractor, we can indicate 30 degrees, and we know this length, and we know that means we can using the compass we can draw a circle here, and then we know already here 30 degrees, and then we find the A prime, and then using against the compass we can adjust the length here AB, and we can draw another circle like this using compass, and we can find the B prime, and then we have the new position of the member 2 using the graphical way, and here we did the same without calculations. But in this example, we are able also to calculate, if it is necessary, in an analytic way, we are also able to calculate the distance between A and B, or the length A and B of this triangle. So those type of calculation and drawing we use very often in these lessons, and therefore these exercises are very important. You have to get used. So, okay, then the graphical position analysis again. You see here the solution. The question was, from the point B to B prime is given already from B prime, and we take the compass and we sign the circle here in this distance, and using also our compass, and we draw another circle here with the center of B prime. So then this is our L3. So then the new position is new position is like this. That's so this is the new position. Okay. Okay, this is new position, graphical position analysis. So because we already know the length AB, and we know the length BC, and we know the length DC, and therefore it's not a big problem to find the final position. We know that the AB B is be moving on a circle with the diameter, with the radius AB, and C is also moving on a circle with the diameter DC, radius with DC. So then we can easily find the B prime and D prime, because we know also all other lengths of the members. Okay, so now here we have an example. So graphically determine the angular lift of the wheel. So this is the wheel here. And you see, this is a wheel. The lift, the wheel assembled as the crank is rotated 60 degrees. Where is the crank? So this is, let's say, the crank. Crank should rotate 60 degrees counterclockwise. So let's say the counterclockwise means so in that direction. It is moving so in that direction. And the motion must be, this is the 50 degrees, and then so the position is 15 degrees. So we have to add 60, then it makes 75. So like this, we'll come to this position. This is the new position. Let's say this is the 60 degrees here. 60 degrees. Okay. So the new position, since the crank, let's say here A, B, this is C, and this is, let's say, D. A, B, C, D is a four-bar mechanism. And we have here the DC is expanded, and we have here, let's say, the point K. And this is also the DK, DCK is a solid part. So it also undergoes a circular motion like this, circular motion with the radius of dk, circular motion. So we know all the distance here. We know the distance of this member, this, let's say this is the crank, and this the length is this member, and we know also the length of this member here and the length of this member here. So we all know that. And here this distance 127 millimeter. So using the compass and protractor may be okay here to indicate the 60 degrees. So we can easily draw the new position graphically. Okay, another exercise. You have to do that, huh? This exercise you have to do at home. You have to finish it. You really have to draw it. So the second exercise, also we have here graphically determine the amount that the door open as the lever, which is originally set to 10 degrees, is rotated to 40 degrees. So let's make 10 minutes break. And 10 past to 2, we meet again. Huh? 10 minutes, only 10 minutes. So, okay, we can continue. So this was our exercise. We said in this picture shown on the screen, we have to graphically define the new position or draw the new position. What is given? Given is the geometry, like you see in the picture here, all the dimensions, and then the angle here, the position position angle of this member here, of these links, 10 degrees. So if it is rotate 40 degrees, as given amount of the graphically determine the amount of the original degrees to rotate 40 degrees. So the question in which direction actually is not necessary, isn't it? Huh? Would you like to ask the question in which direction, clockwise or counterclockwise? Because it's not necessary, you see. You cannot turn it clockwise. Because clockwise, that means, so in that direction, so it is not possible. Because you see here, it's already, the door is closed. Huh? There is no way to move in that direction. So there is no way to move in that direction. So it has to be, this is not possible here, 40 degrees. So it has to be turned the counterclockwise, like this here. Eh? So if we turn the member here, the counterclockwise, then it moves in that direction. This is correct. Free can move. So then it has to be turned. How much? You see here 40 degrees. So 40 degrees, then it will make, so around this point, this is a fixed point, grounded to this body here. So 40 degrees is maybe like this here. It's around here. So 40 additional 40 degrees here. 40 degrees. Because it says, which is originally set to 10 degrees, is rotated to 40 degrees. In total, 50 degrees has to rotate. So in that direction, and then we have to draw the position for the 40 degrees. So also you have to do that as homework. You have to draw it in the first one and the second one. Okay, then we have third one. So the in third exercise, we have here what is saying? It's saying that graphically determine the distance the cylinder contracts. Which cylinder? This one, huh? Contracts when the foot pedal is rotate. Foot pedal is this one, is rotate 25 degrees counterclockwise. That means from the current position counterclockwise. So that means in that direction. Huh? So counterclockwise and how much? 25 degrees from the initial position, 25 degrees. So determine the distance the cylinder contracts. So distance the cylinder contracts, and this is the cylinder here. You may guess what is it. So there's a there's a cylinder, pneumatic cylinder, I guessed. And if you operate this foot pedal here, so you produce the pressurized air from here and into the I don't know, somewhere you use the pressurized air. So you have the distance here, 300 millimeter, 225 millimeter, and 200 millimeter. That means all the these dimensions are given. So the initial position, we have to draw, we have to draw the coordinate system somewhere, and we say if it is, let's say, here the XY coordinate system like this is fixed, this is also fixed, doesn't move. This is X and this is Y. And then, of course, the angle is important here, initial angle. So, and then turning the foot pedal in direction of counterclockwise, like here, counterclockwise. So we have to calculate the new distance here. That it was 225, like here. New distance we have to calculate. Okay, this is also homework you do. So another exercise here. Graphically determine the amount of rotation of the support link when the linear actuators, let's use the laser pointer, where is it? Okay. So graphically determine the amount of rotation of the support link when the linear actuator is retracted to a length of 400 millimeters. So which one is the linear actuator? Linear actuator is retracted to a length of 400. So which one is the linear actuator? What do you think? Okay, so those are the support links here. And those are the support links, they turn. They will turn in that direction because this is the linear actuator. Let's use this color. This is the linear actuator here. So this green one, linear actuator. I guess the tandem telescopic cylinder. So the length for the time being is, or for this instance is 533, and we have to reduce that into the length 400. So 400 means, so the length, these lengths here will be reduced in that direction, and will 400 around. So 400, and for the 400, so we have to calculate the angle here. Angle is the amount of the rotation of the supported links. Those are the supported link here, two supported links. Let's also color this one with the color. We can use this one, huh? So, and this is here. So the rotation has to be calculated. This is the ground. You see here, we can see this is this color. This is the ground here. Okay. So, and this is the mechanism, and this is also here. Actually, it's a parallel mechanism. You see another member, we don't see that, is is this one here. And it's a parallelogram. That means the distance here, 200, here 200, must be also here 200. 200. And here we have 500, on here also 500. And here also 500, given already here, 500. So 500. Okay. So you have to calculate it. All dimensions are given. It is possible to calculate if we, let's say, retract the linear actuator here into the dimension 400 from 533 to the 400. So then we have to calculate the angle which rotates the amount of the rotation of the supported links. Okay, this is also homework. You will do that. So limiting position. So what is limiting position? What we learned till now, so let's summarize shortly. So we learned what is the position, what means changing of position, displacement, and what means the analytical calculation of the new position, what means graphical drawing of the new position, we learned that. So now the limiting position or the limit position. You may remember this mechanism. This is a crank slider mechanism. Like this here, we already discussed in our previous lessons. This is crank slider mechanism and inline. That means so we have here a slider with a joint here, revolute joint, and here we have, let's say, a crank, and this is the coupler. So, and if we rotate this here, crank is rotate with a certain angle. Let's say this is the angle here. Phi. So, and this the slider or piston moves, it makes the linear motion, moves, let's say, the horizontal left and right. So what are the limit position or limiting position? Let's say this is A, this is B, and this is C here. So what do you think, what are the limiting positions, configurations of a mechanism that places one of the follower links in an extreme position? What are the extreme positions here? So the extreme positions are, so let's think that this crank is making, let's say, the circular motion like this. Huh? So circular motion. And this is the point here, make circular motion. Okay. And the slider here, let's use another color. Slider is making here, the slider making linear motion. So moves in that directions or in that directions. So we are interested to define the limiting position. What means limiting positions? So limiting position means if crank and coupler are in line like this here. Let's choose the color here. So the red one. Okay, here. And this is the, it was AB, okay, we said B. This is B prime. B prime. And C will, let's say, will be here somewhere. Huh? This is C prime. Or let's change, say this is B1 and this is B1, this is C1. Okay, so then this is one of the limit position. That means the slider can move maximum till to this point and finish, cannot move more. Therefore, it's a limiting position. There is a limit there. On the other side, if it is turn and arrive this position here, I mean the crank arrive this position, then the slider moves in that direction and arrive maybe this position here. Let's say this is C2 and this is then B2. B2. And this is also a limit position. That means till this point. So during the crank makes its full rotation, the piston or the slider can move between C1 and C2. Maximum, this maximum distance here is, let's say, delta S stroke is maximum here in between. So this is an important definition. If you try to design such a mechanism with a linear motion, maximum, let's say, 20 millimeter or 100 millimeter or 150 millimeter, I mean the delta S, the stroke, so you have to consider it. Later on, we will talk about the synthesis. So how can we design the mechanism? Because in some applications, so maybe you need to define this distance here. So how much should be? So imagine you are designing a machine and you need a linear motion, and this linear motion you are trying to realize using a crank slider mechanism, and the linear motion, stroke of the linear motion must be, let's say, the 200 millimeter, so maximum 200 millimeter. Let's use the okay writer, maximum, so 200 millimeter, exact 200 millimeter, huh? So then, so how should you design that? I mean, at the end you have 200 millimeters, and the length of this one, and the length of this one, I mean the crank and the coupler. So all those things. So you know the limiting positions, or using the limiting position, you are trying to design the mechanism or define the mechanism or define the, let's say, the dimensions of the mechanism. So here, the configuration of a mechanism that places one of the follower link in an extreme position is, you know, is this is okay. This is not in line. You see, this is not in line. There is a distance here between. This distance is 38 millimeter. This is not like this with the draw here. This is the simple one. This is like this here. And the slider undergoes the linear motion somewhere here as to be defined. This is not nice. I have to redraw it. So let's say this is the okay, and we have the slider here somewhere. And here we have our crank and the coupler. So now we have to define the limiting position for this mechanism. So again, we said that the crank here makes rotary motion around the point, around the center of the circle here. So this is the circle here. And so what are the limiting positions? So limiting positions are where the crank and coupler come into the same line. And this is, let's say, the member 2 and this member 3. And member 2 and 3 must be in the same line. So that means then let's assume that the position is somewhere here. And so it must be like this, huh? So this is one of the limit position. This is the point here. Let's say this is the A and it's the A1 here. A1, okay. And then this is the coupler here. And this is the point, oh, this is the point, this is the point, let's use the same notation. What's going on? It's completely removed. It's interesting. I lose the picture. Okay, doesn't matter. So let's. Why is it like this? Okay. So let's do it once more because I lose the picture. So, okay, let's draw the mechanism once more. So I said this is an offline mechanism. That means, so we have here the point A for the crank. This is the point A. And this is the crank here. Our crank. Let's say this is the point B. And the slider, which makes linear motion horizontally. Let's assume that here somewhere. So this is our coupler. Okay. So we were talking about the limiting position. This is the offset here. So, and then in order to find the limiting position, let's use the color red one. So we know that AB is rotating around the point A. And the point here, let's say this is the point C, A, B, C. C is making linear motion. So the linear motion here, like this, on the surface or ground. So limiting position we achieve if we bring the crank and coupler in line. So this is the member, let's say 2, and this is the member 3, and we bring them in line like this. So if we take our compass and open the compass with this distance AB plus AC, then we can make a circle here, somewhere here, like this. And then you will see, we will draft a new, this will be the distance here from here to this point. So, and this will be here somewhere. This is the C1. And so here, this is the B1, the new position, and this is C1. And of course, the other position will be somewhere here, against inline, like this. And for that, you need actually, by subtracting of the length AB from BC, so you can draw a circle here, and then this must be the same here. So this is B2, was B1, B2, and B2 and B2, and this is also here, maybe C2 somewhere. Huh? C2, and this is the coupler here, length of the coupler. It is of course, you see, the drawing is not nice, I know that, but you know, it is very difficult to try to draw using the mouse. But I hope you understand what I mean. So limiting positions are important here. We are talking about the limiting positions, limiting position of this mechanism. That means the crank and the coupler must be in line. That means in line, and there is two positions. One of them is the add together crank and the submission of the crank and coupler. The other position is if we subtract from the coupler to the crank, we bring that in that position. So okay, so that's the way how can we define the limiting position of a mechanism, 4-bar mechanism, of course. Huh? So we have a mechanism. You see, it's also 4-bar mechanism used for different purposes. That means we have here crank, and here we have the follower, and the coupler here, dimensions are given. So configuration of a mechanism that places one of the follower links in an extreme position. But extreme position, that means, so maybe we have here some particles or some objects we use to press or to cut or to, let's say, the disturb or any other purpose. So in which position could the follower arrive? And what is the limit position? Of course, we can say the limit position is this one. So this is the limit position. This is the limit position because, you know, this is the fix here. So this is the limit position. But if we consider the particles in between and dimensions of the particle, let's say this is a nut, for example, walnut, for example. And then we have to say, okay, this dimension is like this, so, and we have to press a little bit in order to break it. So then we can define our limit position. So in that way, so this is our limit position in order to fulfill the function to cut the wall and so on. But this is really final position because we cannot move more because it's already here. We arrived the let's say the final distance because of the ground. So for that, is it I use against the so we have to also define the position of the crank here. So in which position we achieve this function, and the angle we have to move in order to fulfill the function. So all of them we have to calculate. We have to calculate. So we know the dimensions here: 120, 180, 400, and 360, and 60, and so on. So coming from the limiting positions, what are the limiting position of this mechanism? So let's assume this is the dimensions of this nut here, walnut of maybe, I don't know, 10 millimeter or 10, between 10, 15, and so on, and so on. For that, you have to define the limiting position. So this is also homework for you, huh? So this we discussed today. We actually in our last lesson, the lesson before our last lessons. So when we were talking about the vector calculations, so it was the last lessons, correct? Yeah, last lesson. So we talked about the vectors and vector calculations, and we mentioned also the love of cosine and the love of the sine, which are very useful in trigonometry, and we will use also in the calculation of the mechanism. So therefore, you have to learn it. So please, if you see that, don't behave that you are seeing first time. This is not correct. This must be this. Oh, I have to correct. This is not. Sorry for that. Here must be square, huh? So there is something wrong here, or that means it must square root. So I have to correct it here. Let's write here 2. Okay, then bring it here. 16. Okay, so okay, now it's correct. C square is equal to A square plus B square minus 2AB cosine C. So, and sine law is sine A. No, A over sine. This is also something strange. So it could be also, but then we have to write not. So then we have to write, wait, this is 1 over here. Then we have to write 1 over. So 1 over 2r. That's correct. So. Correct, yes. If you write sine alpha over A and sine beta over B, then we have to write here also 1 over 2r. So it's okay. And this is the correct one, huh? So, and therefore, if we write in that way, so we have to write, 1 over 2r. This is the radius here. It was a mistake, so I need to correct it like this. Okay, so then we will continue analytical position analysis. So our next lessons, we will discuss the analytical position analysis inline crank slider. And we will see how can we calculate all the positions, maybe for a full rotation or semi-rotation, all those things. But we will discuss in our next lessons. So till the next lesson, I wish you a nice week. Do you have any question? So please do the homework, okay?